Perfect.
Okay, great. So, well, first of all, thanks for inviting me here. This is my first time on the Telluride workshop, so that's very exciting, and I look forward for the questions. Please interrupt me anytime if you have questions. So today we'll talk about the interplay between motion, eye movements in particular, and visual perception. So, and also the level of control that the visual motor system exerts over eye movements during periods of fixation. So, as we move away from the center of gaze, usually visual acuity and other function gradually deteriorates. With increasing eccentricities. Yes?
Good morning. I'm on a Zoom.
Yes.
Can I just ask a quick question?
Okay, if it's quick, yeah.
Can you?
I just muted Terry for you.
Oh, sorry. I thought he was asking a question.
That's okay.
Okay. So, yeah, so visual acuity and other visual function gradually deteriorate as we move away from the center of gaze. And so we humans compensate for this limitation by relying on a tight link between perception and action. So we perform 2 or 3 saccades every second to bring the object of interest at the center of gaze within the central fovea. So I don't know if you so managed to see the video. Maybe it's a little bit choppy and delayed through Zoom, but here just showing eye movements of an observer looking around as seen. However, the eye is constantly in motion. So even in the periods between saccades, during this brief period of fixation, the eye continues to move. And here is just an example of this motion. You can see it. The eye keeps jittering. Even when the attended stimulus is already foveated, is already attended and at the center of gaze. As this suggests an even deeper coupling between visual functions and oculomotor activity during fixation. So how much does the eye move during fixation? Well, let's take a fixation here. The circle here that you see, that's about 1 degree in size. And so that's about the size of the central fovea, the so-called foveola. So that's the region where cones, photoreceptors are most densely packed. It's free from rods and capillaries. Here is a reconstruction of the amount of retinal motion that the retina is exposed to during this brief fixation period. You can see it, but basically fixational movements generate a substantial amount of retinal motion that would be immediately visible if it was the result of motion of objects in the scene.
Martina.
Yes.
I have a question for you.
Yeah.
Isn't this kind of sustained fixation on one point a very unnatural thing for people to do? Extremely unnatural to do sustained fixation on one point that's not moving around.
Yeah, that's a great point. So the reconstruction that you see here, it's actually just a brief period of fixation. Yeah, so in between saccades, when the subjects just look around the scene. So this is probably around like 200-300 milliseconds. That's usually about the duration of fixations during like free viewing. So yeah, so even during those short periods of fixation, you do have substantial amount.
But you can also track a moving object, so there's also smooth pursuit.
Yes, but that's a different, that's a separate class of eye movements. So here I mostly focus on the eye movements during fixations when subjects are not pursuing an object. So that's smooth pursuit is a little bit larger scale. So here we're talking about eye movements that are moving the stimulus within the central fovea. If that addresses your question.
Yeah, it's clear.
So here is an example of the distribution of gaze position during, in this case, a sustained fixation period over 10 seconds. So yes, this is a little bit unnatural, but it shows you how much gaze over that period of time spans. And it can span an area that is about half degree square during fixation. This is just for one observer. So what are the causes of this motion? Of course, these are fixational eye movements. This retinal motion is the result of fixational eye movements, which come in different varieties. And so we normally distinguish between microsaccades, and these are sort of like small jerks of the eye. They are like saccades, but at much smaller scale. So we define them as being smaller than half a degree. So they basically maintain the stimulus within the fixated object within the central fovea, the foveola. And they are very fast. And then in between microsaccade, the eye still is not stationary, but it keeps jittering. And this jittery motion that sort of resembles a random walk, it's called ocular drift. And you see here an example of eye movement. So as you see, motion, the motion, the stand of motion it's really, within 1 degree of visual, well within 1 degree of visual angle. So these eye movements, fixational movements, are often labeled as microscopic, but that's mostly because from the experimental perspective, they are difficult to measure and to characterize, especially ocular drift. However, on the retina, they sweep the image over many photoreceptors, as shown here. So once again, they create a substantial amount of retinal motion. So to study these fixational movements and their level of control and their contribution to vision, we need the high precision eye tracking. And so pretty much all the data, almost all the data present today, they've been collected by means of a high resolution dual book-inch image eye tracker that we have in the lab, and which is coupled with the gaze contingent system display that we custom develop in the lab. And so together, these two systems allow us for high precision in the recording of eye movements, and also higher accuracy in the localization of the line of sight.
Yeah, incidentally, this is like high precision eye tracking. This isn't like your TOBI, T-O-B-I, usability tracker that you stick on the computer, to track, advertising. This is really like the
I just throw a slide in here, but I'm happy to talk more about our system. We recently developed, the lab developed a digital version of this dual book-inch image eye tracker that you see on the left here. It's great that it's extremely flexible and allows us high precision, so we can reliably study these small eye movements. So the question is what is the contribution of these fixational eye movements to visual perception, and to what extent are they controlled by the visual system? So let's start by looking at microsaccades. So to examine the contribution of microsaccade to particular fine spatial vision, we devised a task in which we asked the subject to perform fine discrimination. So we presented gratings within a narrow aperture, as you see here. So these small apertures are only measure only 5 by 20 arc minutes in size. So stimuli were really small and present at the center of the display. These gratings were presented in a sequence. So first, the grating on the left appeared, and then the grating on the right appeared. And we presented these gratings at different eccentricities within the central fovea. Okay, so we tested 5, 10, and 15 arc minutes. So stimuli were always well within the foveola, the very center of the case, but the slightly larger distances from the preferred locus of fixation of the observer. So the task of the
By the way, Martina,
yes,
just for the beginners here, when you're reading normal text, what is the size of a letter E in minutes? You know, on normal text, isn't that about 30 minutes of arc? When you're reading, like,
yeah, approximately, I would say. Okay. Yeah. So this is much like
really small.
way smaller than that. Exactly. So we're talking about like really high acuity vision here. Exactly. Good point. Yeah, I give these things for granted. And okay. So what's the task of the participants? Participants have to tell whether the two gratings that, remember, they are presented in a sequence, first on the left and then on the right, whether they are tilted in the same way or in a different way. So they are always tilted 45 degrees either to the left or the right. And then we have two conditions. So in one condition, to eliminate the influence of fixational eye movements, the stimuli were maintained at a fixed eccentricity throughout the course of the trial using retinal stabilization. So retinal stabilization, as shown here, it's a technique that our system, that we can achieve thanks to our system, and we're basically moving the stimuli in real time to compensate for the observer eye movements, in this case, fixational eye movements, so that the stimuli, as shown on the right side, on the retina, on the foveola in this case, remain at the fixed position throughout the viewing time. And then we had another condition of normal viewing. So this is a traditional condition in which the stimuli are presented at a static position on the screen. They don't move on the screen, but because of the physiological instability of the eye, they move all over the foveola because of fixation of eye movements. So let's see how subjects.
So Martina, I must have missed it here, but what's the job of the person? Simply to fixate, or are they supposed to do a task here?
Yeah. So let me go through the task again. So they're presented in a sequence, these stimuli, and then subjects have to tell whether the two stimuli, the two gratings, basically were tilted in the same way or a different way.
Parallel or orthogonal.
Exactly. Okay. So it's like a discrimination.
Is the grating moving?
No, the grating is a
fixed
fixed grating. Exactly. Okay. And the presentation was about like, I think around like 500 milliseconds. The first grating appears, and then under 500, there is a gap in between, and then under 500 milliseconds, the other grating appears. Okay, so results. So what we find is that under retinal stabilization, so again, when the stimuli were maintained at a fixed location on the retina, the foveola, performance decreased at larger eccentricities within the central fovea. So already at 10 or 15 arc minutes, performance dropped. And so this is an important finding because it already shows that, well, fine spatial vision is not uniform, even within the central fovea, even within this small, 1 degree region of the visual field, but it already deteriorates. On the other hand, results looked quite different when the stimuli were viewed under normal viewing conditions. Because what happened in this condition is that performance remained approximately flat, where it was higher and remain equal, almost virtually equal at all the eccentricity tested. So to understand why this happened, we examined the oculomotor behavior of the observer during fixation when they were performing this task. And what we found is that microsaccades in particular were responsible for this, improvement in performance under normal viewing conditions. In fact, what we found is that, you can see the movie here, is that microsaccades were precisely controlled, and they shifted the gaze back and forth based on when and where the stimuli were presented. So here on the side, if the movie doesn't work, on the left, you see an example. It's basically the same version of the movie, but static. The blue traces represent ocular drift, periods of ocular drift, and the red traces represent microsaccades. And so the microsaccade shifted the preferred retinal locus on the stimuli, on the details, on the small gratings, very precisely. So this behavior, this is just an example of one trial, but this behavior was extremely consistent across all trials, particularly for larger eccentricities, and also across subjects. And so thanks to this precisely guided microsaccades, then also visual performance in this task improved at the larger eccentricities compared to the stabilized condition.
Just to clarify this, so I understand it, you're saying that basically people look back and forth very accurately between these two gratings to judge whether they were parallel or not, even though the thing is moving around.
Exactly. Well, the grating is fixed. I mean, this is under normal viewing condition, right? So the grating is fixed on the display. And
they're really good at popping back and forth.
Exactly. The subjects are extremely good at controlling these small eye movements. So we are talking about eye movements that are in the range of 15 arc minutes and 10 arc minutes. So really, really small. But apparently there is a great level of surprising level of control that our visual motor system exert over this small eye movement, these microsaccades. And so the results of this study really show that, first of all, fine spatial vision is not uniform within the central fovea, within the foveola, but it starts to drop sharply with increasing eccentricities. And that eventually microsaccades are finely tuned and they reposition the detail of interest on the locus of highest acuity, on a small region within the fovea where acuity is highest. Now, in a more recent study, we showed that this oculomotor behavior, this level of control over microsaccade, is particularly important also in normal viewing conditions because eventually it enables visual exploration of complex foveal stimuli just during the brief periods of fixations. So in this other study, instead of using boring psychophysics stimuli like gabors or gratings like I just showed you, we use more natural stimuli, and these stimuli were faces, human faces. We asked participants to perform two different tasks. So in one task, we asked them to judge gaze direction of faces, so whether a face is looking at you or away. And another task, using the same set of faces, we asked the participants to judge whether the face is smiling or not. Now, this is a trivial task, right? But we showed the face to be just 1 degree in size. So basically just cover the size of the fovea, the central fovea. So just to give you an idea, that's the size of your index fingernail at arm length. And this is what happens. I mean, we are very used to see faces, and so we view faces at all different distances. And it happens many times that we look at somebody standing many meters away from us. So this is what happens, that maybe face is just 1 degree, about 1 degree in size. And so the distance between the different features of the face that we can still, discriminate is just a few arc minutes. Okay, so what we did is that while subject performed this task, we examined and we recorded at high resolution the oculomotor behavior during fixation. So they were simply showed the stimuli and asked to perform the task. So hopefully you can see this movie. This is the average to the gaze position across the subjects that is evolved during the course of time after the stimulus onset. And so, as you see, despite the small stimulus size and the fact that the stimulus was already foveated and eventually ideally placed within the foveola, subjects visually explore this stimuli. And this visual exploration was different and was modulated depending on the task. So, and it was carried out mostly by microsaccades. So when we looked at the landing position of microsaccades in this task, we found that most of microsaccades landed on the mouth when subject judged this expression of face. And this pattern, flipped completely during the gaze direction task, when microsaccades most of the time, almost always, landed on the eye region.
Yeah, but Martina, can I interrupt you here?
Sure.
I
yes.
see here a big blob here right on the tip of the nose. I agree that mostly people seem to look, at least I look at people's mouths, you know, not their eyes. They say in the books, the eyes, but in reality, it's the mouth that is most expressive. But why is there a big peak here right on the tip of the nose?
Yeah, that's a great point. So there are, so some people tend to look at the nose first and then go down toward the mouth. So there's still quite a lot of focus on the nose for some reason when we have to judge the expression. When we have to judge gaze direction is that this is clearly not the case. What is interesting is that we found a very similar pattern also when subjects were asked to view these images at a larger scale. When the image was spanning like 4 degrees in size, so a larger image. What we see here is that there are also some differences across subjects in these visual scanning strategies, and they are maintained across scales. So maybe there are some subjects who tend to look more toward, the nose region, regardless of, especially in the expression task, but they do so even when the image is larger. So it's basically the behavior is maintained across different scales. So these findings basically reveal that active spatial exploration extends also to the foveal scale, even during these brief periods of fixation, and that the visual motor system possesses a fine control over these microsaccades. And that eventually the strategies that we use to explore this complex foveal stimuli are very similar to the strategies that we use to explore the scene at large. So there's quite a lot going on during this fixation period. So the eye is not just simply sitting there and acquiring passively information. So the contribution of microsaccades to fine spatial vision is that they enable this sort of like visual exploration of complex foveal stimuli, and they recenter precisely stimuli, the detail on the point of maximum acuity. So now that we have explored the contribution of microsaccades to visual perception for spatial vision, now let's look at the other component of motion, fixational motion. So the periods in between microsaccades. The eye is still moving, and this motion is characterized by ocular drift. So hopefully you can see this. This is just an example of a drift of an observer just during, again, a brief period of fixation. And as shown here, ocular drift resembles sort of like a random walk. It changes direction frequently. It moves in sort of erratic manner. When we examine the correlation of instantaneous velocity in the two eyes, so the right versus the left eye, we found that during these drift periods, the motion of the two eyes is not correlated, both for the vertical and the horizontal component of motion. So during fixation, the two eyes move sort of independently. Here, just an example of the two traces from two eyes. And so this sort of reinforces the predominant view that pictures that portrays drift as some type of random motion over which the oculomotor system has very little or no control at all. However, we should say that to reliably measure drift, we study drift in a very unnatural setting, because in all our experiments, the head of the observer is fixed, as shown here. We pay a lot of attention in really making sure that it's really well immobilized using headrests and white bar to avoid any sort of head movements, because that would reduce the precision of our recordings. And so again, this is an unnatural condition. Normally, our head moves quite a bit, right? So even if we are sitting still, the head moves. There's significant amount of motion, and even during sort of fixation periods in which the head is still, there is motion of the head, not only of the eye. So we call these sort of like fixational head movements. So really, at the end, the visual input, it's given by a combination of these fixational head movements that are well below 1 degree in size, and fixational eye movements. So we wanted to know how ocular drift and the dynamics of ocular drift change in this more natural, if they do, in this more natural setting. We want to study drift in a normal natural condition when the head is free. So to investigate this question, we analyzed data that were previously collected by Bob Steinman and colleagues. This happened a while ago at the University of Maryland, that they developed a revolving magnetic field monitor. So this is a unique device that allows really high resolution recordings of fixational eye movements in head-free settings. It's really unique. We now have Michele Rucci in the lab has developed a system that is pretty much the same as this original system of Steinman and colleagues. And it's unique because, again, it's the only system that allows for recording fixation eye movements with that precision in a head-free setting. So we examined this database of eye movements in which subjects were asked to, very simple task, to freely look at the set of LED targets in front of them. So they were sitting on a table, so the head was fairly still, but it still moved quite a bit. And they looked at a sequence of LED targets. Now, the first thing that we noticed was that the instantaneous speed of ocular drift were well above the speeds that we typically measure under head-fixed condition. Most importantly, what we find, as shown here, once again, we look at the instantaneous speed in the right versus the left eye. We found that the ocular drift in the two eyes now are highly correlated during natural head-free fixation. So if you remember, this is in stark contrast with what we saw under head-fixed condition, when there is no correlation whatsoever between the way the two eyes move during this drift period. So why this happens? Well, to better understand this, what we did is that we examined the head movement pattern, fixational head movement, so that the small motion of the head that occurred during these drift periods while the eye was drifting. And what we see is, as shown here, is that there is sort of like compensatory behavior, so that the high and dead movements during these fixation periods compensate for each other. Here you just see on the side an example of this compensatory behavior. You see the animation. And so that's what is driving the two eyes to be sort of moving in a correlated fashion during fixation. Now, this compensatory mechanism is extremely important. So you might wonder, why do we need such a compensatory mechanism at this small scale? Why it's important? Well, it turned out to be quite important because in the absence of this compensatory mechanism, then the amount of retinal motion that we would experience a fixation would be dysfunctional for fine spatial vision. So here we compared the retinal motion that is produced during the examined fixation periods. So that is generated by the combination of head and eye movements during fixation. With the retinal motion that we obtained by sort of artificially decoupling the eye and head movements during this fixation period. And so this manipulation effectively led to higher speeds of the retinal image. And so eventually at these speeds, the projection of the stimulus would move far away from the preferred fixational locus during the brief course of fixation. So it's definitely dysfunctional for vision. And in fact, similarly to what has been reported during head-fixed viewing, the retinal motion that results from high head compensation lightens the input to the retina. So what this means is that during fixation in a natural world, the temporal modulation to the retina eventually contain equal power over a broad range of spatial frequencies, as shown here. And what is interesting is that eventually this whitening effect is lost when this fixational eye head compensation is artificially eliminated. So the whitening effect is lost.
Could you clarify what you mean by whiten? I want to give a little feedback control here.
Yes.
So you mean this eye movements here, this is a plot of power versus spatial frequency?
Yes, exactly.
Of the scene.
Of the scene. So let's assume we have a natural scene, right? So natural image has like a 1/f spectrum. That's a typical spectrum of natural images. So if we kind of jitter this natural image based on the sort of dynamics of ocular drift, modulations of ocular drift, then what happens is that we have this whitening, so that the power at the lower spatial frequencies is reduced here, is flattened, and so you have equal power over a wide range of spatial frequencies. So that's
but what makes you think that's good? Is that, I mean, that's an observation, but do you regard that as beneficial somehow?
Yeah, we think it's definitely beneficial because there are a lot of redundancies that are especially present at the in the low spatial frequency range. And so yeah, and especially for for fine spatial vision, to see the details of the image, you want to reduce also the level of noise.
Okay, so I don't quite understand. So you're saying by moving the eye around, you flatten the spatial spectrum. How can a movement in time flatten a spatial power spectrum?
Well, so
must be missing something.
Well, so we take the image, right, and then we jitter it based on the dynamics of ocular drift, and then we look at the power, the average power at different non-zero temporal frequencies, and this is the average power at non-zero temporal frequency for different spatial frequencies.
In this video, basically this video that is now jittered. Okay.
Yeah, exactly. Yes. Yeah. And so again, this whitening effect is lost when this compensatory mechanism is not there. So basically, what this shows that the ocular drift is correlated in the two eyes. Well, when the head is free, right, and this eye head microscopic movements compensate for each other, but this compensation is not perfect. So it results in a residual amount of retinal motion that eventually is functional. It's in a functional range for fine spatial vision. Now, I just want to examine a little bit more in detail the contribution of drift to visual perception. So
Martina, I'm really sorry, but we're like way over time. So maybe I'd rather that you go into discussing what you've shown and answering the questions with the audience than go open loop like this, more into material, unless you want to have a key point that you're missing.
Well, it was more further elaboration on this issue of enhancing by spatial frequency for drift. So, but I mean, I can address question, and eventually maybe some question if they address this point, I can.
Okay, so maybe you could summarize the results here, and then we'll go to discussion with the audience of what it means for Telluride.
Sure.
Okay.
Okay, so I can just be brief and summarize a little bit these latest findings, but because I think they are relevant for fine spatial vision. So this is a little bit summarizing what I said before. So if we take an image, in this case it's a white noise, right, and then we jitter it based on ocular drift. and then we examine the sort of the spectrum of the visual input, what we see is now that there is a peak in the higher spatial frequency range. So in this particular case, given this specific drift, this peak is around 8-10 cycles per degree. What happens is that if the eye drifts a little bit slower, so a little bit less, then these peaks tend to move toward higher spatial frequencies. Okay, so let me just skip a few things. So when we say smaller or larger drift, we really measure it using a diffusion coefficient measure. Okay, so that's basically describing how rapidly the line of sight tends to move away from its current location. And just a couple of slides, what we see is that there is a great variability, okay, across subjects in the amount of diffusion constant for ocular drift, as you see here. So it varies over a factor of 5 across subjects. And so what we thought is that, well, if there is this variability in ocular drift, then and the ocular drift enhances different range of spatial frequency, high spatial frequencies, depending on its diffusion constant, then maybe we might see that different subjects perform differently in fine acuity, in high acuity tasks, depending on their drift. Okay, so I skipped the task part, but if you want, I can go more in detail later. And so basically what we found in a high acuity task is exactly that. So subjects that have a smaller diffusion constant, so they drift less, their drift is more, is smaller, small contained, they also are characterized by higher acuity. The subjects that drift more, so they span a larger area during this brief period of fixation, they tend to have a lower acuity. And so this is sort of like coherent with this kind
Interesting.
of